นลินทร์ครับก็
Good afternoon, everyone. Welcome to Tah Poe Seminar. So today we have our speaker, which is Dr. Pongwit Srisangyingcharoen. He is going to tell us about Faraday's lines of force as springs, an alternative description of Maxwell theory. So let us welcome our speaker.
Okay, thank you for an introduction. Today I'm going to talk about the Faraday lines of force as string and an alternative description of Maxwell theory. And as the name suggests, I'm going to use the string theory to construct the theory of line of forces as the classical electromagnetism of the Maxwell theory. And for the today talk, this is the outlines of the talk. And I'm going to first introduce you. I'm going to talk about the historical aspect of line of force and Maxwell fields. And then I'm going to give you a bit more in string theory. It's going to be very introductory. I'm not going to touch much about the calculation. And then move forward into the topic. And first, I'm starting with the easiest case example, which is the electrostatics, and then move to a more interesting scenario with the time-dependent electromagnetism, and then going to summarize and give some remarks. Okay, let's first talk about the historical review on the Faraday lines of force and Maxwell fields. Okay, let's go back to the 19th centuries. Okay, in 19th century, a lot of physical theory at that time, like Newton theory of gravity and like Coulomb law and Coulomb laws are mostly based on the concept of action at a distance. But some scientists is not happy with this concept of action at a distance, and one of them is Michael Faraday, and he proposed the concept of and the idea of the line of force as the basic description of the physical theory, and he believed that in order that the two separated objects to interact to each other, it can communicate to each other via the imaginary line of force. And it was believed that Michael Faraday he is an experimentalist, and he worked a lot and he experiments a lot with magnets and electric effects. So he might familiar with the iron fielding pattern under the influence of the magnet. So he imagined himself that the line of force would be the answer for solving the concept of the action at the distance. Okay, but this idea is just a qualitative idea. So he wrote his concept in his books, but there is not much mathematical support. So among the scientists, especially physicists, have not taken his idea seriously, but his idea have a great influence on the Maxwell, the James Clerk Maxwell. He had inspired by the concept of the Faraday line of force, and he started to construct his theory on electromagnetism using the mathematics called the vector calculus. But instead of having the line of force as the basic degree of freedom, instead Maxwell used the degree of freedom as a field. And rapidly, the concept of line of force was faded away and was replaced by the concept of fields, which is introduced by James Clerk Maxwell. And as you know, the Maxwell theory is very well known and very accepted. So the concept of field is very predominant. But that was the history in 100 years ago. But today we have the knowledge of string theory. We have the knowledge of string theory, and it possibly that we could bring the concept of Faraday line of force back to life again. Okay, using the string theory, and in this talk is the majority of the calculation are based on the work by Mansfield in 10 years ago, in 2012, and in his paper, the classical electromagnetism was reformulated using the statistical mechanics of the lines of electric flux, and the line of electric flux, which is the Faraday line of force, are described by the string action. Okay. So before I'm going to the content of this talk, let's talk a little bit on the string theory. Okay. I put the cat here to make it more audience friendly, and you know, even the cat can play with strings. And okay, the key idea of the string theory is that the most fundamental building block of the derivative is not the point particle, but instead it represented by the string. It's a one-dimensional extended object called the string, but it's not the actual string. It's like very tiny, one-dimensional object called string. And the elementary particles or the different species of elementary particles can be interpreted by the vibration of the string, and of course, and in string theory, it contains many states. It can be the state of string can be identified by many elementary particles, such as gauge boson is either non-abelian gauge boson or abelian gauge boson, and more of it is contain massless spin-2 symmetry testless particle, which can be identified as graviton. And some physicists say that this string theory could be the theory of quantum gravity, but that is another topic. It's not the topic that we are going to discuss today. And what is the action of the string? The action of the string can be described by the worksheet. What is the worksheet? Okay, in analogy to the point particle, when point particle move in the space-time, it generates what we call the whirl line, right? And the action to describe the relativity point particle is proportional to that whirl line interval. Yeah, that whirl line interval. But the string is one-dimensional, and when it's moved to the space-time, it generates the 2D. It generates 2D space called the worksheet, and because it's 2D, you can parameterize by two numbers or two parameters. Let's say tau and sigma here. And analogy to the point particle, the proposal for the action of the string theory need to be proportional to the area of the worksheet. This is given by the number critical action, where this integration here is basically the area of the worksheet, proportional to the area of the worksheet. And x, what is x? X is called the space-time field. It is the vector in the space-time but it is the scalar field on the worldsheet. So generally speaking, the action of the string is basically the field theory into dimension. But you can see that it's the number equal to action. We don't usually work in the number equal to action because it contains the square root, and the square root make it very difficult to quantize, to do a quantization. Instead, we will use another action which called the Polyakov action, and this the Polyakov action is given by this equation. Now we don't have the square root here. Instead, it is a quadratic form. It is in quadratic form, which is more easy to quantize, right? If you imagine that we are working in part integral formalism, and we have the exact formalism for integrate this like the Gaussian integration, and in exchange of giving up the square root, we have another field called G. Another object here is called G, which is the metric on. It is the metric on the worldsheet. It's a 2D metric of the worldsheet. So, okay, this is enough for the string theory. Let's move to the content of this talk. So let's start constructing the theory of line of force as the basic description to the classical electromagnetic theory. Let's talk about the most basic scenario, which is electrostatics. Okay, this is the toy model. Let's consider this system where we place two stationary charged particles with opposite charge, plus Q and minus Q at the position A and B, right? And if we would like to find the electric field E, obviously we need to solve the Gauss law, right? And the Gauss law for this system is nothing but the divergence of E equal to the direct delta function, which is the source of the point chart here. And one of the possible solutions for this is the sting-like solution, where the electric fields are tangent to this line or to this contour here. I may refer to this as the electric string, right? This is obviously one of the solutions, right? You can check it easily by putting it back here and start computing, and you will see that it is satisfied the Gauss law. But however, when you need to consider whether if the solution is physical, you need to consider if it satisfies the Faraday law or not, right? The Faraday law in this scenario is just it's just the curl E equal to 0, because we work in the electrostatic. We don't have the variation of the magnetic field, right? But when you plug in the the string solution into this Faraday law, it fails. So that means that you cannot interpret that solution as a physical entity. But what should we do to that? What can we interpret it? So let analogy to the Feynman path integral to the quantum system, where in the quantum system, the particle can have quantum trajectory, right? But the classical trajectory can be retrieved from the average of the quantum trajectory, right? We can do the same from this. We say that maybe the classical electric field can be reproduced by averaging the electric strings here, average over the suitable Boltzmann wave, of course. So at this point, we expect that we could retrieve the classical electric field E from this average and this is the average, and this is the part integral average of the electric string here. So, what is the Boltzmann weight we are going to use? So, let's first try the Hamiltonian for the free particle. Okay, this is the action for the free particle, right? And if we use this action, we can construct the heat kernel. The heat kernel is you can view it as a partition function. This is the partition function, right? Integrate over all the degree of freedom y with this action e to the power of minus action. Here it's called heat kernel is just basically the big rotated of the propagator, right? It's related to the quantum propagator, but here we work in the Euclidean signature. Okay, and with this part integration it is well expressed. You can calculate it easily, right? And you can calculate it, and the result is on the right hand side here. It's nothing fancy about it. And okay, where the S0 is the Hamiltonian for the free particle, which is p squared divided by 2. Okay. Then I'm going to average the string solution over all the possible trajectory. Okay, and you can see that the string solution that is contain the Dirac delta function here. So we can turn this problem into the functional integral, where the functional integral of the source term A, where I introduce another source term here. By you can see easily by functional integral of the A if you get the Dirac delta function here, and putting at the end putting the A equals to 0. This is basically the generating functional. Okay, and you can see that this action here is very familiar, right? This Lagrangian is basically the Lagrangian for the point particle under the influence of the magnetic field A here. So this turned the problem into the particle moving in the electromagnetic field, where the Hamiltonian H0 need to modify to be this Hamiltonian, where the now the operator have changed by putting the vector potential A here, and because H is an operator, so we have two operators here: the momentum operator and position operator Q here. And then we are going to differentiate functional differentiation of this heat kernel here, which is equal to this expression on the right hand side here. What we are going to determine is the functional derivation of the Hamiltonian here. And it's not hard to do it. You can see that the Hamiltonian is expressed here, and by differentiate with the source term A, at the end it can be rewritten as the outer product of the position vector in Ket-Bar notation, where this weirdly looking del with two-headed arrow is defined by this, with del on the right and del on the left. It's nothing but just taking the derivative on the right hand side and taking derivative on the left hand side. So this del with two-headed arrow is defined as this expression. So putting this into this equation, the first equation here, what we have is we have this heat kernel here and heat kernel here. But again, this heat kernel, these two heat kernel, we have the exact formula for that I present earlier. So put it here. So in order to evaluate it, we are going to work in the limit that t is very large. Okay, the capital T turn to infinity in this scenario. When t turns into infinity, the integrand gets suppressed greatly, so it's basically zero. But except for 2 points where the small t evaluated at 0 and the small t evaluated at t. And using this assumption, you can compute the integration easily. This is you can see that these are just the gamma function, right? Integrate from 0 to infinity of exponential and some t up to some power. This is basically the gamma function with it equal to this. And taking the derivative here, you return. This is very familiar, right? This is the classical solution of the electric field in our system of the 2-point system, right? Of the point particle, 2-point particle. Okay, so that means in this scenario, you can interpret the line of force as the fundamental degree of freedom, but it is at the quantum level. When you would like to measure the classical level, you need to do a quantum average of that electric strength. Okay, then let's move to more interesting example, which is time-dependent electromagnetism. Okay, we do with the same scenario, but now we make the 2-point particle, the 2-point charges can be moved, right? It can be moved. So again, assuming that if there are the electric string and the 2-point charges can move, it sweeps out to generate the surface here, the 2D surface here, or I will call it the world sheet surface here. Okay, and in this scenario, the electromagnetic current density J can be written as this form, where the A and B is basically the vector, the position vector of the charge Q and minus Q respectively. Okay. So we have J like this. So we need to, and in this scenario, I'm going to find the solution for the field strength tensor F mu nu, field strength tensor, that satisfies the Maxwell equation. What is the Maxwell equation? Is it here, the Maxwell equation? Partial derivative of the field strength tensor equal to the current density, right? And one of the possible solutions is the worldsheet solution. This is the worldsheet solution. This field strength is supported on the worldsheet, where the sigma here, sigma mu nu here, is the area element of the worldsheet. You can see that it is the area element, but this is the you see that the square side, where psi is the are parameters on the worldsheet here, and this is the area element. But even though we have the worksheet solution for this Maxwell equation, but we need to take account for another half of Maxwell equation as well, right? Another half of Maxwell equation is basically here, but you can try, but you can try by putting it here to the another half of Maxwell equation, and you eventually see that it doesn't work. So again, we can do the same trick as before. Maybe we can think of it that the worksheet solution is just the quantum trajectory, and in order to recover the classical theory, you need to functional average of the solution, right? Okay, we will do that. And the way to do again, I'm going to find the classical field strength tensor by functional average of the solution. This is the worksheet solution. Here, it's supported on the worksheet. Here, you see that it supports on the worksheet sigma. And we are going to average with the string action. Subscript P is the Polyakov string action, and the Polyakov string action is given here. Okay, and we are going to integrate out the degree of freedom of the worksheet of the string, which is the y is basically the space-time field, and G is the metric. But at first, I'm going to fix the metric G at some. I'm not going to deviate the metric G, but just going to determine the functional integral with fixed metrics. Okay. So again, we have the delta function here. We can turn the delta function into we can do a Fourier decomposition of the delta function, turn into the integrate of for momentum and the exponential, right? And here we have the worksheet here, the area element of the worksheet here. We can get rid of this by introducing another source term J. By introducing the source term, we can re-obtain this area element by taking the derivative with the source term. Okay. Okay. Now, what we need to evaluate is this expression here, and now we are focusing on this functional integral, which is the integration of dy e to the power of x prime, where x prime is defined by this here. You see that the first part is a Polyakov action, and this part from the Dirac delta function, and this part from the source term. Okay, what I'm going to do is I'm going to expand the y in terms of the classical. Let's say it expand around the classical solution, classical y plus the quantum fluctuation of y. Okay, and it's turned the equation into, it's turned the functional integral into this, where again we are focusing on this functional integral here, where the s double prime is expressed in here. Okay, now we are going to the measure is on the y bar, and the y bar is a quantum quantum fluctuation. Okay, because it's quantum and you can see that you can evaluate, you can do a functional integral of this a bit not hard to do because this is the well-expressed form, right? It is the Gaussian form. Exponential of the S double prime here, the S double prime contains the quadratic term and contains the linear term. It is basically the Gaussian integral, right? Okay, this is the Gaussian integral. And okay, we then carried out the Gaussian integral with the y of the variable y bar with the Laplacian operator. This is the Laplacian operator. Okay, when integrating out the y bar using the functional integral of the Gaussian integral, we obtain this exponential of the s tilde here. And the s tilde is basically here. Express it in here. Where the g is the Dirichlet-Green function of the Laplacian. G here is a Dirichlet. It is Dirichlet because we are in the reference of the y bar, and the y bar needs to be 0 at the boundary, right? That's why it needs to be the Dirichlet-Green function. And the Dirichlet-Green function of the Laplacian is basically defined as here. This operator acting on the green function equal to the Dirac delta function in 2D. Okay, but this green function is special because this green function is evaluated at the same point. Okay, normally it diverges. Okay, so let's put some let's put some function here. Let's call the function psi as is the value of the green function at the coincident point here. So by having this function here, function psi here, and put it back, okay, here you put it back to this here and expand it. It turns out that your functional average or the average or functional average of the field strength tensor can be expressed as here. And now what we need to do is integrate out k. And when integrate out k, you have the final expression here. It maybe look a bit messy, but let's determine the function phi here. As I said, function phi is the value of the green function at the coincident point. I'm not going to show you the detail how to calculate it, but I'm going to give you, tell you the result of it. It turns out that the function psi here is 0 at the boundary. And when it moves into the worksheet, its value gets very large rapidly. So it ran from 0 at the boundary and going to infinity at some point in the middle of the worksheet, I would say. And so in this case, let me reparameterize our worksheet coordinate. So again, as I said, the worksheet coordinate I use it added psi 1 and psi 2, and I'm going to reparameterize by imagine it as using this psi. I'm going to use this psi as the parameter on the worksheet because it has different value in different point, right? So in this, I'm going to reparameterize the worksheet coordinate. This to be the coordinate of the theta and eta here, where the eta here is proportional to the psi, here, you can see that this coordinate can be viewed as like the polar coordinate in the worksheet, where the theta here is in the angular-like coordinate, and the eta here is the radial-like coordinate, where eta is equal to 0 at the boundary and infinity at the middle of the worksheet, right? Imagine that. Okay. Okay. So this turn this functional average to be this expression, and okay, and now with this newly defined worksheet coordinate theta and eta here, and here by integrating out the eta, from 0 to infinity, what you have is this expression. And again, this theta here, as I said, it is an angular-like coordinate. So this is like the integration of the boundary. It is an integrate along the boundary of the worksheet. So you can see this is like the YCL is the position of the boundary. It integrates the closed loop, which means that we integrate all of the boundary. And here you can re-express it as the derivative of this integral. Okay, and with this expression here, it's not hard to see that it satisfies the remaining Maxwell equation. You see that there are normal derivative here, and it obviously anti-symmetric as we expect from the field strength tensor, right? And as I said, it satisfies the remaining Maxwell equation. So that means that in this scenario, by averaging the worksheet with the string action, we recover the classical theory of electromagnetism. Okay. So let me put some summary and remarks. So the first summary is obviously that we have constructing the theory. We use the technology of the string theory to show that the classical electromagnetism can be interpreted as the consequences of the statistical mechanics of the line of force. So yeah, this is the conclusion, the first conclusion. But this model also inspired another model of string theory. So as you may know, I mean the Maxwell theory is basically the gauge theory, right? And it inspired the construction of the gauge theory and the string theory with non-standard contract interaction. How can we see that? Let's see that by putting this string solution. This is the string solution, right, to the Yang-Mills action. The Yang-Mills action is nothing but the F square, right? The field strength tensor square, and putting this into this, you have this expression here, and you do analyze a little bit more work, you can see that this it appear the Dirac delta function here, which generally zero except for two cases. The first case is where the psi and psi tilde is equal, which turn into first part here, which is proportional to the area of the worldsheet. And as I said, the area of the worldsheet is basically the string action, right? It's a Nambu-Goto action. And the second half, the Dirac delta function can have value when x of psi and x of psi tilde is located at the same point in space. That means that the x of psi is the one point in the worldsheet and x of psi tilde is another point on the worldsheet. If equal, that means the worldsheet contract to each other, right? The worldsheet intersect each other. So the second part is what we call the contact interaction of the string. So with this inspiration, there is another work by James Edwards in 2014 that he reformulated the QED, which is the abelian-Yang-Mills theory, right? The abelian-Yang-Mills theory, or the QED here, as the model of string theory with the contract interaction. And in his work, these two models are equivalent to each other via the calculation of the Wilson loop of the QED. He showed that the Wilson loop of the QED is equivalent to this partition function of the string. This is the string action. Here you see that this is the Poyakov string action, and this is the contract interaction that I mentioned earlier. Okay, although there are works on formulation of the QED, but the generalization to the non-abelian theory is still unknown. Okay, there are some few attempts to generalize this to the non-abelian theory, but now it's still on progress. And the challenge of it is because in non-abelian theory, we need to have the field, we have the Lie algebra value, right? Because in non-abelian, we have like the field in non-abelian theory, like it needs to have charges, right? Which is the charge in Lie algebra, right? So in order to have this, you need to introduce another field, which is the Lie algebra field, into the worldsheet. And by introducing field into the worldsheet, you need to impose the dynamic for that. And what is the suitable dynamic for that is still working. Okay. And as I just mentioned this because I'm now a little bit touching on this area too, and working on the generalization of this model to the non-abelian theory, and maybe in the future we will see if it works out. Okay, and probably this is the end of the talk. Thank you.
Any questions?
Just a quick question. So for electrodynamics with string action, right? So you're saying the whole point of this is that you can trade half of Maxwell equations by using string-like solution and then arranging over it like path integral.
Yes.
So then my question is in this picture, So now should I think of this string-like solution as its own particle? Because string theory is like thinking of a particle is instead of a point as a line. Yeah. And this string-like solution follows string action.
It follows string action. So that means you can maybe possibly. I'm not sure about it, but you can say that maybe the string also vibrate and can be interpreted as the particle, but that particle would be the off-shell particle, like because it's like you need to be quantum average in order to it to be on shell. I'm not sure is that the answer. That maybe possibly because when we integrate we need to integrate all the degree of freedom that means we are accounted for every possible string involving in the intermediate step, right? So, and because the string follow the string action, so I believe that if you can interpret it as a particle, it would be off-shell particle.
So normally now it's like just a formal solution.
What do you mean by formal solution?
Yeah, I don't know how to think of a force line that follows the string action. That's my problem. Thank you. Yeah, that's
Any other questions from the audience?
Okay. Thank you for a nice talk. I just curious how you interpret static electromagnetic or configuration of electric field can be obtained from this approach or not? Because you show me just only 2 points of
Yes.
the chart, right?
Yes.
So if the chart continuously like EM.
I see. So, yeah, you curious whether it's just it's true for all system, right? So, to be honest, to be honest, I believe it's true, but yeah, to expand to expand in all in general cases, you need to integrate all the trajectory and the string are not fixed at the 2 point. You have the string from this to every point possible, and that you can think of like each point communicate via the string, and each pair there are string attached, right? And you need to integrate all of the string, and it requires a lot of work. I'm not sure is.
For example, for the simple one, that is like a single chart.
So for the single chart, you can start with the two chart and then putting the one chart to infinity, and I think that would be the approachable method. Or you can think of that string at the string that one point at the source and another point at somewhere at infinity.
Any other questions, especially from students? Okay. Maybe a very naive question for me. So your string size solution, it has a singularity for the whole string, right? Or at some point.
It have the Dirac. You mean like the Dirac delta function?
Yes, because of
So-
the Dirac delta function.
So the Dirac delta function is put there because we need to make sure that the string is tangential to the string, to the contour. So we are interested in this string solution.
But the value of the function is not infinity. Or infinity.
It is the integration. I don't think so because it is like actually the integration. So it have the value at the point, but zero at outside. Here you integrate. This is like you integrate. This is a line integration. Here, right, this is a line integration here, and the integration of the Dirac is just putting is basically the putting value to the line.
So it has got value at the point.
Yes.
But not anywhere.
No. So you may think that it's continuous distributed value along the line here as this expression here. You know, it's already integrated. If you integrate out the y, it is no singularity. Like y is a three vector.
You're supposed to get x. No, just one. Right?
Sorry.
You are supposed to get.
Yeah.
I'm a bit confused with the integral here. But anyway, there is no singularity. Okay, and you mentioned that the Bianchi identity, the del mu f mu rho. Yes, that
This
one.
one.
So you mean this equation is not satisfied?
Yes, it's not satisfied. So it will satisfy at the end. You see that there are many partial derivative here, but at the end it's got partial derivative here. And when you put it back to that, it's not hard to show that it will sum up to zero.
But before you do the quantum average, so it looks like is there a magnetic charge basically?
Sorry?
Is there a magnetic charge? I mean, because this equation is not satisfied, so I'm expecting something kind of like magnetic charge on the right hand side. Maybe I'm wrong.
You mean magnetic?
Yeah. Because the F does not satisfy this equation, so
Yes.
It should mean that there is something on the right hand side.
Oh, I mean, this is the Yankee identity. It just show that, but when you put it here, it's not zero. I mean, you can say that it's slash.
Yeah, I mean, it's not zero. It means there should be something on the right hand side.
It should be, but I don't know where it is.
So I'm not sure if it's going to be related to some
Not sure about that too.
Thank you for answer. Are there any questions? No? Okay. So Let's just thank our speaker again.
มีขนมอยู่ข้างนอก
There are snacks outside if anyone would like snacks outside the room.
Please have
Please help yourself for the snacks.